Thank you all for attending today. My name is Patrick Hope. I'm a product specialist here at Siemens. I would like to spend some time today talking to you about material properties and board simulation. I would like to start by asking you all the question, what's the point in simulating if you build something different? Then I plan to spend a few minutes answering my own question. First of all, let's talk about simulation in general. Simulations aren't meant to be a one-to-one modeling solution. They're a tool. The right model in the right place is key to successful simulations throughout the life cycle of a design. In general, simulations are used to resolve two main issues. They're used to develop design rules, that is, to determine and refine our overall design rules to figure out how we are going to route the board from stack-up design through to breakout and via monitoring and connector monitoring. And to verify designs before fabrication, that is, to ensure the board will function as routed. Our goal with HyperLynx is to perform the most accurate simulations possible in the most efficient way possible. But before we start with our simulations, we need to develop what we call a single source of truth. This starts immediately after part selection is complete, and it's generally driven by your most dense array. This will dictate your overall layer count and determine which layers contain critical nets and just generally build your overall loss budget. This single source of truth exists as what we refer to as a spec stackup. And all of your simulations that you're going to build your board on are based on the assumptions you make here. How accurate this spec stackup is depends upon how diligent you are in your data process. If your end goal is to have your fabricator ultimately build your board without relying on the design you create here, then all your simulations have started out incorrect. Our goal with zPlanner Enterprise is to build the most accurate stackup possible, to have it reflect real materials, and to have it built upon the actual fabrication process that will be used to construct the board. The stackups you build and the material you choose at early stages of design simulation are important. Here are two measured loss curves for identical designs given to two different fabricators. When measured, these boards are clearly very different and have very different characteristics at 10 gigahertz. In this instance, the reason why is because the two fabricators used different copper roughness values on the core side and did different oxide alternative treatments on the prepreg side. This seemingly minor difference can cause significant effective frequencies in the multi-gigahertz range, and not controlling your material characteristics early can make a huge impact on your overall loss. If you are spending a significant amount of time modeling and performing detailed simulations on incomplete data sets, what on earth are you doing? What is the point of that? So the first reason we simulate is design simulation. This is where we develop our design rules. It's the point where materials really begin to matter. At this stage, you may have a general idea of your board thickness. You may have DK, DF values in place so you can perform calculations based upon. But are those values based in reality? Do they represent an actual material? Does your fabricator have it on hand? There are any number of other factors to consider with the design simulation. I just spoke of copper roughness effects. Another great one is understanding the weave of your fiber in your dielectric. The fiber and resin have different electrical characteristics from one another and cause signals to propagate at different velocities, potentially causing what is known as glass weave skew. There are any number of ways to mitigate this, most of which are featured in one of the chapters of the ebook which we provide, but many of the mitigation methods are material dependent. zPlanner Enterprise offers an absolutely massive dielectric library that allows you to construct very precise measurements against actual material properties. So you're building and simulating with an actual material that has a specific resin content, thickness, weave area, DK, DF values, a specific TG value, specific type of copper etch, etc. If you are developing your design rules without this information in place, how accurate are those rules? And at what point will they have to change? After routing, we come to a post-layout verification simulation, where we work to determine if the board can be fabricated. We are looking to determine our operating margins to see how closely those rules we set in place during the previous slide were followed, and where we test for outliers. When I'm performing a simulation based on an actual layout, I want to be able to compare like results. I don't want to have one format from pre-wrote and a completely different format from post-wrote, where I literally can't just compare the numbers. To ensure this is the case, I want to return to the idea that we've been working with a consistent set of data, the single source of truth, throughout this process, that our stack up and the materials themselves are vital to the verification process. So, when we look at the methods for verification simulation, they fall into a simple methodology. First, we create a topology models for all the signals, and then we use the same simulation method as design simulation to determine our operating margins. So were the design rules we determined previously followed throughout the layout? A project manager may argue that the point of creating the design rules was to follow the design rules. Why spend time creating them if you're going to break them? The rules may be realistic for getting your design to a prototype, but they may be unrealistic for a full production run. But if they don't get followed, or perhaps they can't get followed, how would you know? How do we know what changes took place? Well, we rely on our single source of truth to bridge the gap that exists between design and manufacturing, and then we verify our design after it has been routed to ensure that we have simulated what we are going to build. In our methodology, we start by running electrical design rule checks during layout to look for common problems. Then we're going to use standards compliance analysis to look at the system level interconnect and make sure it meets protocol requirements. And finally, only once we've gotten as many problems off the table as possible, we'll use IBIS AMI or a vendor-based model simulation to predict how the system will perform with actual devices and settings. We call this methodology progressive verification, and it allows us to find layout problems as early in the design cycle as possible with as little effort as possible. We deliberately separate verification into different stages so that we can defer time-consuming and expertise-intensive analysis, allowing us to make the best use of scarce SI experts. We start with simple analysis, then add accuracy in controlled stages because the time needed to model and analyze the system increases as we make the analysis more accurate. That's true with any tool, not just zPlanar, not just HyperLynx. The time and expertise needed to perform simulation increases dramatically as analysis accuracy goes up. If we want to visualize that verification a little more closely, it might look something a little bit like this. On the bottom here, we have accuracy. And over here, we have the effort required and the expertise required. It's also relative to the number of people capable of performing the process. Post-road verification within Siemens runs within a methodology we call progressive verification. It represents 3 fundamental steps which increase in complexity, simulation accuracy, and the time and effort that goes into them. They can be seen as sifting out progressively finer issues within your design. And it starts with electrical design rule checks. This is exactly what it sounds like. It's sort of a visual check to ensure that your design process fundamentally followed the rules in place. It's essentially an instantaneous process that you could conceivably just do by looking visually for common problems if you have enough time. The computer can do it, like I said, almost instantly. Is my spacing correct? Are my widths correct? Things like that. This is tasked to sort out all the blaring issues. The majority of issues flagged through DRC are going to be immediately obvious to the designer. You'll look at it and it'll either be obviously an issue or it will obviously be fine. And as things are flagged, you'll be able to sort them like this. It'll be pass, fail. There will be ones that skirt the line that will be of concern here. Something you look at that you say, oh, I don't know if that's going to pass or fail. And those are the ones that will continue on in the process. The next step is standards compliance analysis. This looks at the system level interconnect to check it against protocol requirements. This helps us to determine if our issue meets the compliance characteristics of the issue at stake. Did a channel pass or fail? If so, by how much? This can be run using one of absolutely hundreds of protocols and variants that Siemens supports, 235 at our current count. This should help to weed out a lot more of the issues with somewhat minimal total time. We can perform this test as a 2D simulation or a 3D simulation. This again starts to get into the granularity of the results versus time invested. A 2D simulation is much quicker to set up and perform, and anything failing on a 2D test will certainly fail on a 3D test. But a 3D test requires more time and is more accurate. And finally, we have the vendor IBIS AMI simulation. Once these two methodologies have weeded out the majority of the problems, then we use this IBIS AMI, or vendor-based model simulation, to predict how the system will actually perform. The system allows us to find problems as early as possible in the design cycle. If we are finding basic problems with the IBIS AMI models, then we are wasting our time. The earlier the problem is found, the less work it was to find, and it keeps the specialized SI engineers' involvement until late in the analysis process. This separates the expertise required for post-rote verification, allowing the majority of the issues to be resolved by system designers and not specialists. Now let's look at a more practical real-world application of this verification process in work using real materials. The board we're going to be using for this demonstration is a dual-socket server motherboard based on the reference design for Intel's 4th generation Xeon processor. This design has 16 DDR5 memory channels supporting a total of 32 DIMM slots. It has 10 PCI Express 5.0 channels operating at 32 gigatransfers per second. That's a total of 336 serial channels that are going to exist across our simulation. And those are the data points that we're going to be looking at in a moment here. So Intel has provided a list of requirements for the interface. And this lists the PCI Express ultra-low loss strip line value at 0.96 dB per inch at 16 gigahertz. This is the requirement that we're going to be looking to meet when we're simulating this board. One of the materials recommended for this specific board is within the ThunderCAD line from TUC, and it's specifically TU885, an ultra-low loss material that they provide. We're going to look at the simulations using the actual characteristics of this material. One of the interesting things to note in this sheet is that while TUC doesn't list their prices, they do provide a cost ratio for the different materials. So we're going to be able to do a comparison on the performance of the materials based on their cost. Within this demonstration, we're going to focus on TU885 and TU883C specifically to perform the simulations. With zPlanner Enterprise, we can isolate and examine their properties. Here we are seeing a plot of their DF values as a function of frequency. This plot involves 5 different materials. We can look at this and quickly discard at this point other potential materials just based on their initial performance within the software here. Here we are discarding EM528 and IT968G. And then we are going to plot the 3 remaining TUC materials that we shown in our previous slide into this radial diagram. This radial plot of their key parameters is 16 gigahertz, which is our target frequency, shows the DK, DF, TG, and TD values of the product, as well as the z-axis of coefficient of thermal expansion for them. So we're able to visually compare the materials here. Using zPlanner Enterprise, we can quickly take these options and build stack-ups out of them and push them through simulations with HyperLynx. Again, we are going to simulate based on the board that we showed previously that has a total of 336 serial channels. This is a graph showing the performance, and we have the spec in the red dotted line showing the eye width and eye height values of the requirement. This specific example is from a 3D solver running overnight on a single rack. You can get similar comparisons in an hour or two if you run a 2D solver on your laptop. From here, we get a much neater picture of what's going on. We can see the interface requirements in red showing the eye size. And here we see plotted are the higher end materials, TU885, alongside the lower cost, TU883C. So if you're performing at those costs and looking at these numbers, it's important to realize that this represents a significant savings between the two materials with relatively little trade-off. Thank you so much for your time today. And remember, serial link design and verification is easier with zPlanner and HyperLynx.